So we were saying in previous lectures how much n equals 4 differs from a phenomenologically inspired theory. And we said, and we were comparing with QCD, but it could be with any theory that is more or less of phenomenological interest. And we said, look, the main differences are in symmetries and in field content. And yesterday we were discussing ways of overcoming these differences. And most of the, in symmetries, the differences are, as we discussed, this theory is maximally supersymmetric, has what's called an R symmetry. This theory is conformal, while these theories typically are non-conformal. If supersymmetric, minimally supersymmetric or no supersymmetric at all, they do not have an R symmetry, but they have what's called a chiral symmetry or a baryonic symmetry. So yesterday we were and field content-wise, this theory has all the fields in the adjoint. So there are gauge fields, scalars, and fermions, all of them in the adjoint of some SUNC gauge group. While this theory has gauge fields in the adjoint, fermions in the fundamental, typically, right? You may admit some fermion in the adjoint, but typically phenomenologically inspired theories do not have scalars, right? So, and I'm saying this in the house of Higgs, but okay, we didn't measure any scalar. Okay? So yesterday we were trying to address this point of the symmetries by constructing duals or inspiring duals that where the conformal symmetry is broken, at least part of the R symmetry is broken, and supersymmetry was also broken, right? So we discussed examples where we had DP branes for P different from 3. And in all those examples we discussed normalization group flows, right? And we saw how in terms of this radial coordinate, this flow is very nicely realized, right? We discussed examples where one is starting from some n equals 4 theory, but then deforming it, either by inserting some operator or giving bed to some other operator, okay? And we said typically the operators we are inserting are relevant and they will drive the infrared, they will change the infrared, right? So the theory flows into a more interesting quantum field theory. And we said the dual perspective to this, the way of doing this in ADS-CFT is to start with a background of the form ADS5 crosses 5, deforming in the sense that this is a solution of containing a metric and a 5 form, deforming in the sense of turning on the other fields, in this case in the type 2B string, okay? Turning on some of them, all of them, etc. Let this solution flow and get some metric, some configuration, background, let me call it. And then proposing that this background contains the infrared aspects of this theory, and that this full background contains encoded the strong coupling view of all this flow. Okay? And we saw one example of this, one explicit example of this. Okay, then I mentioned another way in which people have gone over this breaking of symmetries. That was this idea of wrapping branes. Okay? The example, the particular example I was mentioning was one example where one is taking a bunch of NCD4 branes. Okay? on NCD4 branes, just let me remind for you, on them, a field theory in 5 dimensions. A field theory in 5 dimensions, leave, or 4 plus 1 dimensions. This field theory contains a gauge field in the adjoint, contains 5 scalars, contains 4 fermions, and contains a potential. Okay? And from this viewpoint, this field theory is not at all interesting for phenomenology because it lives in the wrong dimension and has the wrong field content. But the idea was to take these 4 branes and do something tricky on them that was basically compactify them. Let me see, how can I do this so that you can still see this? People in the back, can you see her right here? John, see? Yeah. So the trick point here was to compactify these D4 branes in a way that was very reminiscent of finite temperature things. Though it's not finite temperature what I'm doing here, but it's a compactification on a circle where I'm giving to all the fermions antiperiodic conditions on this circle, and to all the bosons periodic. This will imply that the system preserves no supersymmetry, which is good. Okay? This one here was preserving lots of supersymmetries, 16 supercharges. This will imply that the low energy field theory, so we discussed a bit about the spectrum of this, and we got to the fact that in terms of, in an energy scale, there is a massless gauge field. By the way, this is the weakly coupled spectrum. There is a massless gauge field. There is actually a massless scalar, but it doesn't talk at all to all the other fields. Just let me tell you in a minute where it comes from. And then after a gap, and this gap is related to the size of this circle, you will find a set of scalars and fermions, just like in any Kaluza-Klein compactification. They will typically be non-degenerate, and there is a tower like this. And this tower is well studied in the literature, etc., etc. So the interest of this field theory is that if you look at it at low energies, right, so with long wavelengths, you will not be able to detect that you have this extra dimension, and your field theory will look 4-dimensional. In that sense, it's in the correct dimension. Will have no supersymmetries. And then you start pumping up the energy a bit more, and you will start seeing the effect of these ones. Okay? Right? So if you go to high enough energies, what you will see is a tower that starts to appear with some periodicity, right? And you will recognize they are an extra dimension. All right? But the idea of this is to construct a dual, and we did this yesterday. I wrote a metric yesterday, a metric that is representing this situation of the 4 branes being wrapped on a circle with periodic and antiperiodic conditions. And the idea is that then this metric is going to be describing the strong coupling dynamics of this field theory. Okay? So yesterday we wrote a metric for this. We wrote a 4 form, and the decathlon explicitly in terms of the things of the metric. I don't think I will need it now, so let me not write it. So this was just an example of wrapped branes that, as you can see, is a qualitatively different example from something like this, in the sense that when you go far in the ultraviolet, the field theory has a ultraviolet completion that is not a conformal theory as it will happen in this case. Okay? It's not a 4D conformal theory as it would happen in this case, but in this case it's just a higher dimensional theory. Okay, so I was planning for today to do two different things in the 2 hours that we have. One of the things I was planning to do was to describe, though this I can certainly avoid, and maybe I can ask now what people prefer. One thing was to describe one system similar to this one, qualitatively similar, where one is using D5 brains, one is wrapping them on a 2-sphere, and is preserving minimal supersymmetry in 4 dimensions. Okay? So it's a good dual to a field theory whose field content, whose weakly coupled field content, is a gauge field and a fermion, both of them in their joint, and then a tower of supersymmetric scalars and fermions and massive vectors, all of them supersymmetric. Notice that supersymmetry is preserved not only at this level but at each of those levels. So that's one example I could discuss about. And the other example I could discuss about is a very nice one by Klebanov and many collaborators that is more in this line of thinking, in the sense that your ultraviolet completion, unlike in this example, or unlike in this example where again is a higher dimensional field theory, your ultraviolet completion is a kind of a conformal point. Right? So you go, when you pump up a lot the energy, you look like you are in a conformal theory. So I was planning to discuss this and this, and then in the other hour, I was planning to discuss the following thing. Notice that all these fields that I'm mentioning here, all these fields of n equals 4, right? Even when I flow, are all fields that live in the adjoint representation of the gauge group. Okay? So if I start there with those fields in the adjoint, whenever I deform and flow, the fields will still be in the adjoint, right? Because I'm not introducing new matter. All these fields on DP branes, they live in the adjoint of the gauge group of the DP brane. So in the next hour, I was planning to discuss a bit about how to change the field content by adding fundamental fields, adding quarks, in other words, okay? By adding fundamental matter. So I had an ambivalence that is the following. Either discuss that thing of the fundamentals, or discuss some relation that was found not long ago between this kind of setups and this kind of setups. They look apparently very different, but there is a very cute geometrical relation between them. You can go from one to the other by just geometrical operations. That's kind of geometrical, while that thing is more physically motivated or motivating. So we will see when we go from this room to the next what we do. But meanwhile, let me describe a bit about these 5 branes or this Klebanov system. Okay? So given that you are now not tired, I think it's better to describe the Klebanov system that is technically a bit more demanding. Okay? And since if it catches you tired, it's more difficult to understand, so let's describe the Klebanov system. Let me see if I had something super marvelous to say about those wrap 5 branes. No. It's horrible. Yeah, okay, there is something that is very nice, but I will not say it. So let's describe this. Let's describe this Klebanov system. So the idea is to start not with an n equals 4 conformal theory, okay, but to start with an n equals 1 conformal theory, minimally supersymmetric conformal theory. By the way, the reason why supersymmetry enters in all this is mostly a technical reason, that is the following. In all the things that I'm mentioning, one is always, one way or another, finding a solution to the equations of motion of some type 2b or type 2a supergravity, right? So yesterday we wrote the solution that is corresponding to this. Today I could have written the solution that corresponds to this, okay? These solutions are increasingly complicated, okay? The one that I wrote yesterday is kind of simple. One could have guessed it within 1 hour. This one, you don't guess it within 1 hour. You have to be more into the thing. This one of Klebanov, you certainly do not guess it within 1 hour. You have to work harder. So the reason why people go for supersymmetry, and this, I'm just talking to the young part of the audience, is because when you have supersymmetry, you have a very easy way to find equations of motion that are simpler to solve in the following sense. You will find first order equations. People call them BPS equations. Bogomolny, Prasad, Sommerfield. That solve the second order equations. Okay? So it comes for free with supersymmetry that instead of solving nonlinear coupled second order equations, you will be solving nonlinear coupled first order equations. And believe me, it makes a great difference. Okay? When you are into the business, it makes really a difference. So that is basically the technical motivation for why people will keep on always typically a minimal amount of supersymmetry at least. It's just a technical point, but simplifies a lot the calculations, truly a lot. and probably doesn't change a lot the dynamics. Okay, so coming back to Klebanov, Klebanov proposed, let me do this historically, Klebanov and Witten proposed a minimally supersymmetric conformal theory in 4 dimensions. That if you are not familiar with it, let me be a bit clear about what is it. So there are 2 SU and C groups. Gauge groups. So there are gauge fields in each group, and it's supersymmetric, so you will have what people in the notation usually call a supersymmetric gauge field. It contains a gauge field and a fermion, and there are 2 of them, 1 and 2, with another gauge field and another fermion. They will transform in the adjoint of one group and in the adjoint of the other, and will be completely neutral under the other group. Okay? And this system has a set of global symmetries that we will see in the gravity side in a moment, but let me write them. So there are 2 SU2s, right? One that people call left, one that people call right. A U1 symmetry that is called U1R, typically characterizing supersymmetric theories, and a baryonic symmetry, just like the baryonic symmetry of QCD, if you will. So you see, there are the gauge fields that they are completely neutral under these SU2s. They are completely neutral under the baryonic symmetry, and just let me mention it as a matter of technicality. The fermion has R charge equal to 1, right? So just to put it correctly. And same for this one. They are completely neutral here, has R charge equal to 1, and is uncharged under the baryonic symmetry. Then you will have these 2 fields that they transform in the fundamental of one group and in the anti-fundamental of the other, and vice versa. these ones in the fundamental of one group and in the anti-fundamental of the other. Let me call them A1, A2, and B1 and B2. So there are these 8i and bi fields. So they transform in the fundamental of one group and in the anti of the other, and vice versa. These ones, this believe me at this stage, these rotate under one SU2 as a doublet, and they don't rotate under the other. And the opposite happens for these ones. They have R charge 1/2. And one has baryonic charge 1, and the other has baryonic charge -1. Okay? This field theory, in order to be conformal, should be supplemented by a potential. People in supersymmetry write things in terms of what's called a superpotential. Basically, the relation is that the potential is the derivative of the potential with respect to the fields, different fields, squared. Okay? And this superpotential is the following. Something that I will write in the following, just for commodity, in this way. But the contraction of the SU2 fields, the 1 and 2, is given by these two epsilon symbols. Okay? So okay. All right. So just to be more clear, these A1, A2, B1, B2 are supersymmetric multiplets. So they contain one scalar component, one fermionic component. Okay, each one of them. Okay, very good.
So you want A sub beta there?
Yes, yeah. A beta, Bj. Okay, yeah. So it's A1. So this is a way of saying A1, B1, A2, B2 minus A1, B2, A2, B1. Yeah. There is a trace, so you can reorder all these things. All this is non-abelian. There is a trace, so it always boils into this. Okay. I lost all the erasers there. Okay, very good. Very good. So let me say a couple of things about supersymmetric theories that should be said in order to grasp a bit what will be the dynamics here. So let me maybe say this here. So I will basically pull out a couple of formulas. They are well-known formulas. One of them was derived by Schiffman, Weinstein, Sakharov, Novikov. It's called Novikov, Schiffman, Weinstein, Sakharov beta function. And the other is just an extension of it, and it's going to be, so one is going to be a beta function for the gauge groups, and the other is going to be a beta function for this coupling. Okay? All right, so we will, there is a point I would like to make that will hopefully become clear. So about this Novikov, Schiffman, Weinstein, Sakharov, the idea is the following. Suppose that you have a gauge group SUN, C, and you have some adjoint matter, whatever you want to have, but you also have a gauge group SUNF. Okay, so you have, aside from your adjoints, some fundamental fields. So the beta function in this case, the beta function for this gauge coupling, takes the following form. And this is going to be the anomalous dimension of the anomalous dimensions of these fields. Right? So you can have something like that. Okay, just to make a theory non-anomalous, we'll put fundamentals, anti-fundamentals, and this is the anomalous dimensions of those fields. And for the particular case of a potential like this, the beta function is, and then I can tell you how you compute this thing, but just let me write it, is, let me see if I can write this nicely. This is the anomalous dimension of the A and the B fields. Okay. Okay. So the point I want to make is the following. Suppose that we apply these formulas to that particular case. Okay. So let's specify these formulas in that particular case, and notice that this double line notation will mean that you will have two fields going there. Okay. So there is the field A1 and the field A2. All right, so let's go for it. If I compute, let me call this group 1. In this case, there is not much of a difference, but it will make more of a difference in a moment. If I compute the beta function of the gauge coupling 1, I will get the following. Minus 3 times n, right? Minus, now let's count the number of flavors. Well, it's 2, right? There are n a's and b's, 2 times n, right? So you could count in this way. There are 2 arrows times n, okay? And this is the anomalous dimensions of the a's and of the b's. They have the same anomalous dimensions, basically due to the symmetries that they afflict equally the a's and the b's. Okay. So let me leave this at this stage, and let's compute now the beta function of the group 2. So it's 3 times the rank minus 2 times the number of flavors I have. Okay? So we have these 2 expressions, and they are of course the same because the 2 gauge groups are the same. And let's compute the beta function for the coupling kappa. Using that both anomalous are the same, the fields are kind of indistinguishable, it's given by that. Okay? So now you may wonder, is it possible to make this beta function vanish all at the same time? Okay? And it turns out that it is. If they take this value, this vanishes, you see this gives you a 3 halves, that with the 2 cancels this, and that's it, okay? Right? But notice that the price you are paying, and it's actually not a small price, but it's a reasonable price, is that the field theory will be, if you want it to be conformal, will be strongly coupled. If not, it's not conformal, okay? Right? The fact that the anomalous dimensions are not 0.10 to the minus 1000, they are not perturbative, that tells you the field theory is strongly coupled, all right? Okay. Notice the following in passing. The fact that the superpotential is given in this way, and thinking on the fact that the dimension of this is the typical dimension of a chiral field, right? That is 1. This is telling you that the potential has dimension, naively, has dimension 4, right? 1, 2, 3, 4. When you compute the potential, it will give you something of dimension 4. So when I do the derivative with respect to one of the fields, I get dimension 3, square dimension 6. And this would tell you that you have a non-renormalizable theory, right? But what's actually happening here is that all this counting is not correct. Your field theory just reaches strongly coupled fixed point, okay? And protects itself from all the problems that the need for an ultraviolet completion would imply. So if it is clear more or less this counting and what's going on, why this theory is conformal, we go on. If not, moment to interrupt is now.
a few things to ask you. Firstly, I mean, how do you see that gamma A is equal to gamma B?
That's because of the symmetries, and you will see it more clearly the moment I write the gravity background. This system has an SU2 symmetry, right?
Yeah.
The A is transformed under one SU2, the B is transformed under the other, and the system is completely
Symmetric on the
Yes.
left and right.
yes, yes, yes. That's what I meant to say, right? Right. This square is the same if you do this. Okay.
So if
So
you have
I will do nothing in this to distinguish A from B,
Okay.
right? So you could make this set 2 transformation. Okay? Let me say it that way. It's not very correct. Say it that way. Tell me the other question.
Yeah, well, I mean, how do you get this second one?
Yeah,
The first one looks like, I mean, usually gives me like things, but
Well,
what about the second one?
you see, these are all results that are typically argued to be one loop good, right? Or this one here, there will be corrections here. If there were no flavors, it's argued to be correct to all orbits.
Yeah.
Okay. By the way, what I'm quoting here is the numerator of the Novikov-Schiffmann-Weinstein. This is what people call the Wilsonian beta function, by the way. How do you get this? It's the same kind of supersymmetric trickery of computing and then realizing that the thing is one loop exact and things like those. It's all very nicely explained in some lectures by Strassler that are called an unorthodox introduction to supersymmetric field theories. Unorthodox introduction. Or unorthodox is in the title. So, okay. Any other questions or comments on this, please?
So on the question about whether beta cap comes from, isn't it precisely the condition that superpotential, correct superpotential, has to have exactly conformal dimension 2?
Okay. So by let me say differently. By if you believe that one, you prove immediately the following. And now I'm coming to you. One thing that one learns in all this supersymmetric story is that the dimension of the field is the dimension that you count classically, 1 in this case, plus the anomalous dimension divided by 2. Yes? So if the anomalous dimension is minus a half, this is 1 minus 1/4, that is 3/4. And now if you count with 3/4, that's your dimension 3 superpotential. Okay? And a superpotential must have dimension 3. This is a bit of supersymmetry, supersymmetric things. Superpotential must have dimension 3 because always appears in actions in this form. If this has dimension 3, this has dimension m to the 4, this has dimension m to the 1. Right? So the thetas, each one counts dimension half. So you see this has the correct dimension. So you may have thought it, let's impose that the superpotential has dimension 3. This will pull out for us a beta function like that. And indeed, there I have a formula that contains factors that would have been confusing to put. When you specify those factors for the dimension of this being 1, this one. And that there are 2 A's and 2 B, this gives you precisely this. So it's another way of getting it. Okay? Very good. Any other questions or comments? We are now going to the dynamics of this. Okay, so let me keep this, maybe. And perhaps the first thing I should say is that Klebanov and Witten not only proposed this field theory, but they also proposed a dual to this field theory, right? So what's the geometry that will capture all that non-perturbative dynamics? And the dual looks in the following way. Let me see what I can copy. Let's do it here. So the geometry looks in this form. There is a metric. It's very similar to ADS5 cross S5, and there is a 5 form. The metric will have the usual topology, the usual drawing, if you want, that we had in the ADS5 case. That's going to be 4 dimensions a radial direction, right? They will form the ADS5 bit. So this will have. Let's now use other coordinates. Okay, that will be our ADS bit. And we need an ADS bit because we are insisting this theory is conformal. We need someone to realize the SO2-4 isometries. But then, instead of having a four sphere, a phi sphere as we had in previous lectures, we'll have another manifold that is called the conifold. And now let me be less confusing, and it reads something like this. I think I don't have it copied there, so let me just do it by memory. The conifold will look something like this. There will be two spheres, and they will be responsible to carry this SU2 and SU2 isometries. Okay? There will be a U1 circle, and it will be responsible of carrying this U1R isometry. And the thing is not that innocent. This circle is fiber over both two spheres. Okay, so the metric will read like this. Let me write one of the two spheres. Let me write the other. And let me write now this vibration. I will use the angle psi to denote that U1. And you see the vibration is with what people call a monopole on this sphere and a monopole on this sphere. Okay? So this is the gauge field of a monopole that lives here. This is a gauge field of a monopole that lives there. Right? So this is what I mean by a vibration. This thing is not completely independent. There are mixed terms between this, and mixed terms between this and this when you do the square. That's what people call a vibration. But anyway, this some of you might be completely familiar with this. Some of you may not. So let me put the factors that will make this a solution.
You don't need some U1 for the
very good, very good. That U1 baryonic is not geometrically realized, but is realized with the F5. Okay? So this F5, so has one component in these coordinates, and has another component in you want in the volume element of this 5-dimensional manifold, this, and this. Okay, so in the psi component of this volume element, that U1 baryonic will be realized. Okay. And as you can imagine, many things can be computed with this particular metric and this particular thing. For example, the thing we insisted upon previous lectures was to compute the Wilson loop. If you do so, if you apply the formulas we develop, etc., it will not very surprisingly tell you that the energy between a quark-antiquark pair in terms of the separation of that quark-antiquark pair goes in a Coulomb-like law, as it should be in a 4D conformal theory. And the law is something like this, with a coefficient here that is related to this manifold. Okay? All right. And it's related to this manifold because this R is related to this manifold. So if you remember, it was appearing in our calculation of A is 5 cross S5, so it will fit back here. So unlike this, people have computed many things with this, but the point here is that this background, it's argued, is conjectured to be dual to this field theory, and this conjecture is kind of strong. It passed really many tests. Okay? So let's go with it. Okay, now the thing is this okay? Is this okay? Can this be followed? Can some of you tell me, because then at what time we have to go to the other room? 4:30, right? Okay, so
Actually,
why don't we do until
It's
4?
not clear until when we have this booked. So, assuming nobody, because we couldn't book two places at the same time, that
Right.
was not allowed. So, I think we might have this until 4, and then we have the other one from 4 to 6, or it could be that this is until.
The other, in the
4:30
paper
and
you
the-
gave me, it was 4:30.
Yeah, I assume that, but that was an assumption based on the fact that nobody should come here at 4 on a Friday afternoon. But
Yeah, I think we're.
Well, look,
reasonably
let
safe
someone
on
show up
Friday afternoon at
and
4, yeah.
okay. So let's stop at 4:10, right? So I just want to show you one calculation that is very visual, and then we can discuss how this visual calculation gets translated into this. All right. So the thing that let me see where I can do this. That is nice. But in any case, we are going to lose these black box. So let's do it in this one. Can people see this? John, can you see here? Yeah. All right. So the formation that Klebanov and Nekrasov in one paper and Seitlin in another propose is doing the following. We'll keep the same type of quiver. We'll take the same numbers that we have, but instead of adding some operator or let's deform this theory. Notice the following. These things were 0 because this number here is conspiring. The fact that this number is what it is, when this being minus a half, is cancelling this, right? So their point is, let's avoid this cancellation by adding here a deviation from there, right? And let's make this deviation not very big compared to n. So let's work first in the case in which n is much bigger than n. Okay? Let's now compute those two beta functions. So, and where we will be assuming, in spite of the deviation, that the anomalous dimension of A and B will still be minus a half, right? Up to a very small correction. Okay, so let's work with that as a good assumption. So if you compute this beta function and we go over that formula there, you will get for the group 1 minus 3n minus, okay, the number of flavors now is 2 times n plus m. 1 minus half. And the beta function for this is 3 times n plus m. Okay, 3 times number of colors there, minus the number of flavors, 2 times n, and here the 3 halves, as before. Okay, so if you do this one, okay, this is a 3 halves again, right? The 3 halves kills the 2 kills itself with the 2. This gives you 3m, and this gives you minus 3m. Okay, all right. I hope that calculation is clear. By the way, this one still gives you a 0 because you see it's not depending on the number of on relative number of so what you see from here is that one of the couplings, now we are going to the infrared, right? One of the couplings is behaving like the coupling of QED, and the other is behaving like the coupling of QCD. Okay, so one will become strongly coupled, one will become weakly coupled, and one will become strongly coupled when going to the infrared. When going to ultraviolet, it's the opposite. But let's go to the infrared. Let's flow as one should flow. Now they're coming. No? Okay.
Right. So we could not.
Let's move.
It's still 8 minutes though.
Yeah.
So. this
Why? But
thing-
they are desperate to
Well, I'm
learn.
sorry.
Yeah.
So
It starts 10 past either way, so.
Yeah.
they start 10 past.
Yeah, it should be. Right.
Well, let's go. Just okay.
Yeah, let's
Just let me say one thing. Hopefully this will be clear. In any case, we will lose this black force. So let's erase this. So, what's the thing here? You see, you will be dealing with one field theory that now let's take only a field theoretical picture of all this, right? Then we can think how the metric behaves. But then first let's go pure field theoretical. You're dealing with one field theory that will go weaker and weaker, and one field theory that will go stronger and stronger. Okay? Let me say this with the biggest amount of lubrication that is needed, because it's a lot of knowledge that comes in this, and I'll say it very quickly. There is something called cyber duality. These are the reasons why I didn't want to talk about this Klebanov thing, because it involves lots of many things about supersymmetry, but okay, it's good to see it. Suppose that you have a field theory with a gauge group SU and C, and a flavor group, and NF flavors. Okay? And suppose that it happens that NF is bigger than NC plus 1. Okay? And suppose that this field theory goes strongly coupled. So there is a dual description, and this is completely within the context of field theory. There is no gravity yet. We didn't talk about any gravity yet. There is another field theoretical description. All this is proposed by Cyber. This is the Cyber dual theory. That has a different gauge group. This is what we discussed in the first lecture. Remember, as an example of duality, the gauge group doesn't matter. It could be different. But it has the same flavor group and certainly the same number of flavors. Okay? There is one subtlety here that another field called meson has to be added, but let me avoid that subtlety for the moment. It's important in here, but not so important as to not understand the thing. So you see, okay, so basically what you are doing is you are taking the number of flavors minus the number of colors, right, in your new gauge group. And this one will be weakly coupled when going to the infrared. Okay, so this is a good one to compute the things that you cannot compute for this. So the idea here is the following. Suppose that you start flowing to the infrared. This theory is very weakly coupled. So with this we will be very happy. This theory is very strongly coupled. So we need something to replace it. Okay? One possibility would be to find string dual, but the simpler one is just to do a cyber duality. So if we do a cyber duality here, okay, this is, you see, this group is so weakly coupled that you can think it as a flavor group, right, as a global group, while this is a gauge group. So the flavors do not change. If it was n, it's still n, right? This is the thing that I'm saying here. The global symmetries do not change. But what happens to this one? Well, you see, I have how many flavors? 2 times n, right? 2 times n minus number of colors. So this will produce for me a group SU n minus n. Is it clear as just an algebraic calculation? I imagine that there are many things for why one should believe that, etc. But is it clear just algebraically? Given a rule, is this clear? Jamie, yes? Right. So you see that you started from this group. And after this duality, you went to the infrared and you generated this group. Okay? There's a subtlety that I will not elaborate upon now, that is the arrows get inverted. But let me not elaborate on that. If you compute now, it's okay, this Paul, alright? Yeah. So if you compute now, so at this stage you are computing beta 1 was giving plus 3n, beta 2 was giving minus 3n. If you compute now beta 1 and beta 2, right, the beta function for this and the beta function for that, it will give you the following. Which is more or less visual, because I don't know if we still have the calculation here. What will happen is that now we don't have n plus n flavors, but n minus n flavors. So the n's will still cancel and the n will come with the other sign. And same here. Okay? Right. So let's go to the other room. And if you are happy with that, let's go to the other room.